Thank you very much to the organizers for the opportunity to speak this conference. Today I would like to talk about the stability of a quasi-local positive mass theorem. And this is a joint work with Aguila Lai and Steve McCormick. And just as a full disclosure, the flavor of this talk is going to be a bit different from many of the talks of this conference, but I hope you will find it interesting. So let me start by setting up the mood of what I'm going to be thinking about. So consider space-time. For this talk, I'm just going to restrict to 4 dimensions. So we have a Lorentzian manifold satisfying the Einstein equations. And what I'm going to be thinking about is about space like a slice in this space-time. So that is a Riemannian manifold. And of course, if we use the Gauss and Codazzi equations, we can find some geometric constraints to this slice. And this is what motivates a well-known concept, which I'm going to define now, which is an initial data set. So a triple MGK, where MG is a Riemannian manifold and K is asymmetric to tensor, is going to be called an initial data set if it satisfies the so-called constraint equations. For this talk, I'm not going to use much about the structure of the equations. However, I have this slide just to set up some notation. Here, R of G denotes the scalar curvature of MG. K is the symmetric to tensor K that is mentioned in the definition. That if you want to think of it in the context of the Cauchy problem in general relativity, this tensor is going to act as the second fundamental form of MG inside the space-time. T is the energy momentum tensor, mu the time density, and J the momentum density. I'm always going to assume the dominant energy condition, which says that mu is bigger or equal than the norm of J. I'm going to restrict the set of manifolds that we are going to consider today to asymptotically flat manifolds. And let me explain a little bit more about this. So we are going to even simplify the situation here by assuming that we are in time symmetry. That means that the tensor K is exactly 0. So then what we are really interested in is in Riemannian manifolds with non-negative scalar curvature. Moreover, we are going to assume that the metric on this manifold approaches the Euclidean metric at infinity sufficiently fast, and that the scalar curvature is integrable. If we have a manifold of this type, we are going to call it an asymptotically flat manifold. I put a picture here, or a drawing of such a manifold, so you can think of a manifold that maybe in a compact region can be very complicated, but we know that outside a compact set, the metric behaves really nicely in the sense that it approaches the Euclidean metric. If we put all these facts, all these properties together, we have a nice fact, which is that we have a well-defined notion of total mass, which is called the ADM mass. For this talk, I don't need to tell you more about this in terms of how to compute it or what's the expression. So let me go ahead and just give you 2 basic examples. The first one is, of course, the Euclidean space. As you can think, or as you can imagine, the ADM mass of this space is going to be equal to 0. And we have another important example, which is the Schwarzschild manifold, which arises as the t equals 0 slice of the Schwarzschild spacetime. And if you compute the ADM mass of this, not surprisingly, it's going to be exactly this parameter m. So since we have a notion of total mass, it's natural to ask whether this mass is positive or not. And this is the content of the celebrated positive mass theorem, which was proven by Shen Yao and Witten, assuming the spinor condition. And it says that if we have a 3-dimensional complete asymptotically flat Riemannian manifold with scalar curvature non-negative, then its ADM mass has to be non-negative. And moreover, we have a rigidity statement that says that the mass is going to be equal to 0 if and only if our manifold is isometric to R3. And let me remark that we are going to be interested in this talk in the rigidity statement. And why? Because from here, we get the motivation. And our driving question is the following. If the mass is close to 0, can we say that the manifold is close to the Euclidean space? And here the key is what close means, because although this question is very natural, the technical details can be very complex. A precise formulation of this question has been proposed by Lee Sormani in terms of sequences of Riemannian manifolds and convergence with respect to the intrinsic flat distance developed by Sormani and Wenger. There has been a lot of results in this direction. Unfortunately, I don't have time to review them, but if somebody's interested, just let me know, send me an email, and I can just provide as many references as you want. Let me switch now to what I'm really interested in today. So we have seen that we have a notion of total mass for asymptotically flat manifolds, but then it's also a very natural question to ask how much energy or mass is contained in a finite region of a space. A measurement of this type is called a quasi-local mass. There are many types, but today I'm just going to focus on the Brown-York mass. So let me just give you the definition right away. So suppose that you have a closed surface inside a manifold Mg with Gaussian curvature positive and positive mean curvature. Additionally, suppose that this surface sigma encloses a domain omega that has non-negative scalar curvature. Using the works of Nirenberg and Pogorelov in the resolution of the Weil problem, since the Gauss curvature of sigma is positive, there is an isometric embedding into R3 as a convex hypersurface. And this is going to allow us to make the following definition, which is the definition of the Brown-York mass, which is essentially a comparison between the mean curvature of sigma inside Mg and the mean curvature of sigma inside R3. And it's in the form of an integral with a normalizing factor. So this is the notion of quasi-local mass that I'm going to be interested in. And let me tell you about a positive mass theorem for this type of quasi-local mass. This follows from the work of Xi and Tam. And with all the notation I have been using, we know that the Brown-York mass is non-negative and the equality holds if and only if omega is isometric to a region in R3. So again, it's very natural to ask a similar question here. What happens if the Brown-York mass is almost 0? So now let me put this question in terms of sequences as Lee and Sormani did. So suppose that we have a sequence of compact surfaces such that its Brown-York mass goes to 0. Can we say if the sequences of domains converge to a region in R3? And if so, in what sense? Let me give you two examples to more or less the situations. The first one is this very nice situation in which we have a domain, and we see that the domain is being deformed along the sequence in such a way that in a very smooth way, it converges to a flat region. So we can think of this to be a C2 convergence at least. But let's try to come up with different examples. So suppose that now we have something like this. So now you have your domain, and you're going to have this sort of tentacle becoming thinner and thinner and thinner. So then at the limit, what happens? If we consider the Gromov-Hausdorff convergence, we can see that the limit is going to be a flat region with an interval attached to it. So our goal is to find the right topology in which we can actually get convergence to a flat piece. The conjecture is that the intrinsic flat distance will do the trick, and this follows from the corresponding conjecture for the positive mass theorem in the work of Lee and Sormani. Let me briefly tell you what's our main result. So in this type of problems, one first step is to restrict the set of manifolds that you are going to work with. And our approach is to consider graphical manifolds in R4. That is, our compact manifolds are going to be graphical manifolds described by functions on R3 and over a fixed domain U in R3. We are going to allow U to be different, but only in the sense that we are going to allow our graphs to have a minimal boundary. So our result says the following: if you have a sequence of compact graphical manifolds over an open connected bounded set U with non-negative scalar curvature, here I'm avoiding some technical conditions for time reasons, then if the Brongniart mass goes to 0, then the sequence converges to the closure of the domain in the plane R3 with respect to the Federer-Fleming flat distance. Notice this is the flat distance, not intrinsic flat distance. So in the remaining 4 minutes, let me just quickly tell you more or less how the proof goes. So the idea of the proof is the following. We are going to adapt the arguments of Wang Li when they in the way they prove the stability for the positive mass theorem. Let me tell you that this technique was also adapted for the asymptotically hyperbolic positive mass theorem, also to study the stability of tori with almost non-negative scalar curvature, and it was a fundamental step towards proving the intrinsic flat stability of the positive mass theorem. So let me quickly tell you with pictures what's the basic idea. So this is our R4, and this is our domain U, and consider a compact graphical manifold. Then what we're going to do is we're going to find an appropriate height in this graph, which can be shown, or we need to show that it satisfies the following inequality, that the difference between the supremum of the graph and this H0 is controlled by the Brongniart mass of our manifold. Then what we are going to do is to consider the plane at the height H0. Notice that this plane contains an isometric copy of the closure of U. So now what we are going to ask is what's the flat distance between the graph, and sorry, this should be the intersect, or this should be U cross H0. So if you don't know what's the flat distance, don't worry, I can give you an idea of what it is. So what we need to do essentially is to approximate the volume of the regions enclosed by these two graphs. So let me be more precise. In this case, we have 3 distinguished regions, which are the one below the graph and above the plane, the region below the plane and above the graph, and this little tab where we might have a minimal boundary. So now the idea is to estimate these 3 regions, or the volume of the B regions and the area of A. And the volume of B plus and B minus can be seen to be controlled by the mass because of the way we pick the height H0. This little piece A, since we're assuming it's a minimal boundary, it can be seen to be controlled by the Riemannian-Penrose inequality, which is essentially a control by the Brongniart mass. Sorry, it's not the Riemannian-Penrose inequality, it's something very similar to the Riemannian-Penrose inequality. And then by putting all these things together, we have that the distance between the graph and the closure of U at the height H0 is controlled by the Brongniart mass. To get the final result, what we need to do is to make this construction or this estimation for each element of our sequence, and after a normalization in which we bring the plane H equals 0 to the plane R3, then we can see that since the mass of the Brongniart mass of the manifold goes to 0, then the distance between the graph and the closure of 0 inside the plane R equals 3 is going to go to 0. And I'm going to stop here.